Oh, hello everyone, and welcome to another stream here on Freaky Physics, and we are live. We're gonna have another lesson today for review for the IBDP exams. All right, so we will start in a few minutes. Well, in a minute, I guess. And okay, for those who want to listen in again to help with the reviewing, you can join in and see what we're doing. All right, so for that, just join the class right now. Sorry, I joined it fast. All right, okay, let me join now. No wonder I haven't hearing anything. All right, here we go. Okay. quite there yet, so let's wait a few more moments. Okay, so while we're waiting, oh, there we go.
Hello.
Hello, Gita. Good day, and how's everything today?
It's okay.
Okay, okay.
I'm a bit sick.
Oh, I see.
You,
Well, hope you can focus. Get well soon. Right?
yeah, thank
Okay.
you.
All right. Okay. You sent me over a few new problems. One of them is basically one big problem, right? Or a couple of them. All right.
I think, yeah, two
Yeah,
big ones and the
two big
rest.
ones. Okay, so I guess we better start with those.
Okay.
Okay. Uh, hold on. Let me just get to the board. Oh, and then let me share the board with you here. There we go. Okay, so okay. Let's get to that first big problem. Which one is it? 66. All right. Copy. All right. Here's the first problem we'll do today. So you have two isolated objects, and both of them are charged, and they have a certain mass. Okay, so they're the values here. They're suspended by strings, and in most cases, when we say that, strings are massless, so we don't have to think about those for now. Yeah. The objects, though, are in equilibrium, where the angle between each of the strings is the vertical seen here. Okay. Um, we're first looking at the mass, rather the distance between the centers of mass here. Okay. So okay, let's start with this the solution here. Excuse me. Okay, so first of all, let's identify the forces on one of those charges, because it's they're all identical anyway. We can just do it for one mass, right? So we know that the mass of this first object, let's do this one on the left. There's gonna be a mass m, so therefore it's got a weight mg. Oops. Now let's lock that. Okay, there's a mass mg here. Okay, and of course, there is a tension going up like this, right? There's the tension. Um, and then finally, we have a repelling force between the two charges. So that's gonna be your FC here. FQ or FE. Let's label that FE for electrical force. Okay. And what can we? What's the equation for the electrical force between two charges? That's going to be K times. In this case, the charges are identical, so we're gonna get Q squared over the distance between them squared. Okay, so that's the electrical force right there. The tension, what we can actually do here is we can do the free body diagram. We can now do the free body diagram, or we can solve the individual components x and y again for each of those forces. Okay, so in this case, if we're gonna do that, we're gonna do the mg. We're gonna have the tension, and then we're gonna have fe, right? So in this case, the mass here on x is gonna be 0. That's gonna be mg. The tension, we'll get to that in a while. This is gonna be all fe, but negative, because in this case it's to the left. Okay, and then we can put 0 here. Now for the tension, that's gonna be relatively simple. This is gonna be t. So let's put the angle here at 12. So this will be sine of 12 degrees, and this will be t cosine of 12 degrees. Okay, and we know it's stationary, so the resultant force is 0 on both sides, on x and y. Okay, so let's equate the one more thing, mg will be negative here. Let's not forget the sign. Okay, so in this case, what are the two equations we get? We get t sine theta is equal sine of 12 degrees. Let's put the angle straight away. That's going to be k q squared over d squared. Okay, And also we do the other one, t cosine theta, or 12 degrees. That's going to be equal to mg. Okay, now we can do substitution for t, or we can just divide the first equation by the second equation. So if we do this, we do that, right? Okay, so once we do
Um,
okay,
sorry.
go ahead.
The FE, is it cancelled out by the horizontal component of T?
Yes, it is, because
And
it's
then,
stationary.
okay.
All right,
And why do we divide these two?
it's gonna become apparent real quick. The t cancels
Okay.
out, right?
Okay.
But once the t cancels out, we don't have to deal with the tension anymore. In other words, we don't have to solve for t anymore. Okay, now that we've done that, what do we do here? We simply, what's this gonna be? That's gonna be tangent of 12 degrees. Again, simplifying the problem further, right? So we're now gonna just simplify everything. That's gonna be k q squared over mg d squared. And now we're looking for d, finally. So d will be equal to the square root of the whole thing now. Okay, so k q squared all over mg tangent of 12 degrees. We put the values in, we get d. Okay. All right, so let's just do that real quick. So what's the value here? K was 8.99 exponent raised to 9 times the charge. What the charge is, let's go back to the problem. Okay, charge is 5 microcoulombs, so that's gonna be 5 so times 5 micro is minus 6. So let's put, okay, so times 5 exponent negative 6, and then we square that. Okay, then divide by the mass. Let's put that in the mass, mg tangent 12 degrees. So the mass is given as 1.2 kilograms. Let's put that here, 1.2 times g is 9.81. Go ahead.
About the previous question, what like made you think of dividing the two forces? Like,
Oh,
I understand
yes,
we made
yes.
the two equations for the
Mm-hmm.
forces. Why
Mm-hmm.
did you choose a tangent that
It's actually a math shortcut. Okay, if two things are equal to each other, if there are two equations, then you can act. The main thing we usually do is substitute, right? But the shortcut here works simply because if we do the substitution, I'll just do the substitution here real quick, just to show you what's happening. Okay, so if we do substitution instead, we get that t is equal to kq squared all over sine of 12 degrees, right? You get the idea here. We got it from the first, oops, I forgot the d squared here, from the first equation, right? Then I'm gonna put this into the second equation, so I'm gonna get k q squared over d squared sine of 12 degrees times 1 times cosine of 12 degrees is equal to mg, right? 12.
but if we're expressing the force, then
Uh-huh.
we need to take away the weight and like have the resultant of the
Yes, that's right.
x and y.
That's right. But here's the thing. We know it's stationary, so the resultant on both x and y will be 0. So that's exactly what we got here. Right. So this is from the
Hmm.
x. Okay, this is from x. And
Yeah.
then the one at the bottom here, the cosine 12, that's the y, right? Again, that's because of the fact that x and y are both in equilibrium. Because the whole thing is in equilibrium.
Okay.
Okay, so so I think we can see it here, what happens afterwards. This just becomes cosine 12 degrees, and that's gonna be equal to mg, right? So we still eliminate t either way. Now if we move stuff around, to look like this, we'll actually get that same equation.
Yeah.
So one way to actually do the okay, that's just another way basically to do the shortcut. If you can see something cancel out, if you can divide one equation by the other, go ahead and do that. So that's what happened here. Okay, and anyway, think about it this way one more time. This is these two are equal on the numerators, these two are equal on the denominators. So it would still make sense to do division in both, divide one by the other equation, and it still kind of works.
Okay.
Okay.
Yeah.
All right. So okay, going back. So oh, okay, I've already put the value in. What's the final value? Is this the final value? Um, yeah. The D, according to this equation that I got, did I finalize that yet? I don't think so. Let's see. I think I did. All right. Anyway, so that's the equation there. Just put the values for all these KQ, MG, tangent, theta into the calculator and get your final answer. Okay?
Okay.
All right. I don't know what the final answer is anymore. I pressed the equal sign on my calculator too many times.
It's
Okay.
okay. I'll do it.
All right. So I think on the stream we'll see what the final answer is. It's either the first or the second one I've pressed there. Okay.
Okay.
All right. Anyway, anything else you'd like to ask on A for A?
That's okay. I understand that.
All right, great. Okay, so let's go to B. The two large objects are then held stationary inside a vacuum. Okay, and there's no gravitational field here. Let's copy the rest of the problem here. And then there's a small negatively charged particle placed right between those two things. Okay, and okay. Actually, this looks similar to something we did last time, the gravity problem, right? Okay. But first, okay, so here we go. Let's lock this as well. Okay, so what are we gonna do here? So again, let's take a look at the forces acting on Q. So there are two forces from that, from each of the charges, like that, right? And because the charges are equal and the distances are equal to that negative charge, this is gonna be, at least in magnitude, that's gonna be F here, right? Let's just write F in this case. Actually, no, let's not write F. Let's use F1 on both cases. Okay. Now, if we go back here, show that for x0 much smaller than D, the magnitude is this. So this is important here. Okay. Because, where can we put it? Let's put the angle here. Okay, let's put that angle theta there. So we can also do this, that fx should be equal to f1 sine theta, right? And then fy should be equal to f1 cosine theta. And then we're gonna do the fact that it's symmetric on both sides. So in this case, the sum of f along the x-axis will be equal to 0 because they cancel each other out. If it's not clear, it's basically because the signs, the two arrows are gonna look like that, oppositely directed. Okay, but in this case, the fy, the sum along fy, that's going to be equal to f1. Then there's a 2 because they add up, and then cosine theta. Okay. All right, hold on. Before we continue, all right, I think before we continue, I'm gonna change something here. Okay. The reason why I'm changing something is because I already know something that you may know, but may not be aware that you can use. Okay. So I'm gonna put my theta here to make it easier later on. When I realize it, okay, that means I'm gonna have to change this to cosine here, and then sine here, right? Okay. Similarly here, this will be sine right here. Okay. Now here's the thing, though. If we go back here, that's just the That's just the F, right? But we also know that this is an electric force. So we go back to F1 is actually equal to, let's just say that this is a distance, some distance r for now. Okay. Okay. So with that distance r, we know that that's going to be equal to k. There's a k there already. Q, and then q all over r squared, right? Okay. That's strange. Why did we get d to the 6? Okay. Uh, so let's just put that in here. Oops. Okay. So in this case, our actual total force, F, so this is also going to be equal to F, right? So our overall force will be equal to this. Let's just put that in there. 2K, then the two charges all over R squared. So we kind of have something that kind of looks like what we already have, right? What is missing? We're missing the number 128. We're missing the x0 over d to the 6, right? Okay. Um. Okay. Let's continue. How do we get the 128 and then the d6 and then the x0? Um. Let's see if that works. Oh, did I forget something? Oh, I forgot the sine theta. Okay. So, okay. Now let's express okay, before we continue, let me see if I missed anything. No gravity, negatively charged, x0. It can be shown that k or a is large. Explain why releasing this. Oh, okay. Actually, we don't. Okay. Sorry. We didn't really have to prove that. We just have to use this. Okay, I misread the question. We just have to use this, right?
Right. Okay.
So, okay. Use, don't prove. Okay. Okay, that's my mistake on my side. Okay, but anyway, here's the idea. Why would this be SHM? Okay. If you think about this, we'll reason it out here again. The force is basically going to just go that way, and that way again, then that way. That's how it's gonna oscillate, right? So let's change colors. Oscillations again gonna go that way, that way, that way, right? Oscillation. Now, why is it simple harmonic motion? Remember that for simple harmonic motion, um, acceleration is proportional to negative than displacement x. Okay. Okay. Um. Yes. Okay. Why is this approximately SHM? Because if we divide this further, we express A is equal to 128k. Or okay, hold on before I do that. This means that A is approximately to some constant C times X. Then there's a negative sign, right? Okay. In this case, let's just do it here. The negative part, it's already, we can see that the force, and then, where's that? 128k q over d raised to 6 x 0. Okay, x0. All right, now what can you say here? This whole thing is constant. Okay, I forgot the mass, but either way, with the mass there, that whole thing inside the box is constant, right? um is there anything else? I think we can just actually remove the x0 here. Okay, because this is the force right at x0. So what we can use here is that we can say that the force the force is already proportional to x. Okay, and then it's also opposite opposite in direction. So these are the two things we need to say when we see simple harmonic motion. We have to show that either the force or the acceleration is proportional to x, and that those two are in opposite directions. Okay, so that's the long way. The short way to say it is just basically this. Okay.
Okay.
All right. So again, okay, I think that's kind of clear, but not totally at the moment.
Perhaps.
Perhaps. All right. Again, so let me just say it again. Simple harmonic oscillation or simple harmonic motion depends on this relationship, that the acceleration is proportional to negative x. In other words, if you turn it into an equation, it has to be x times some constant. Okay?
Why?
That's the definition of simple harmonic motion. Proportionality, this is the definition, right? Let's go back here. This is the definition. Okay. Now, this basically means if you turn it into an equation, this is also what it means. So this is a proportion, this is proportion, this is equation. They mean the same thing. Okay. Now that C, I'll just point that out here. This C is a constant. Okay. As long as it's constant.
How do we know?
Okay.
How do we know that it's a constant?
That's the thing with proportionalities. The proportionality becomes an equation by attaching a constant to one of those variables. Okay. It's more of a math thing than a physics thing, but yes, that's how it's done.
So if I said I had like v equals to f lambda, and I say v is proportional to lambda, is f the constant?
Yeah. So in this case, v equals f lambda in your case, as you said, right? And then v is only proportional to lambda, so that means f is constant. Okay.
But it isn't constant.
In this case, it's not. That's the thing, though. This is what it means if we follow the logic here. But we know that the constant here, the flaw here, is that v is the constant in most cases. Okay. So that doesn't make sense in this case. However, I'll give you an example here of a possibility. Okay. So a possibility here, doing v equals f lambda, and then v is okay. So v equals f lambda. So possibility v equals f lambda, and then you say v is proportional to f, right? Lambda, right? Wavelength. Okay. Then that means that f is constant. F is constant, or constant f can happen in refraction. What changes in refraction? It's the speed of the wave, right? What doesn't change in the refraction? The frequency of the wave. So it has to mean that the wavelength also changes with it, changes with speed. Okay.
Okay.
All right. So in this case, the idea of proportionality works. Okay. All right. Okay. So aside from that, I think that's the only one really bothering you at the time, right? How did we get this? Everything else is clear.
Yes.
All right, great. So let's go to part 2. We have that data, angular frequency. Okay, let's go back here now, and let's do part 2 here. Let's go back to this, okay, that A is proportional to negative x, right? Now in physics, that C, I'll just write that in equation form, equals negative cx, right? Now in physics, as we know, it should be in the data booklet that C is equal to omega squared. Okay. All right. So with that in mind, what can so we can rewrite this as actually a equals negative omega squared x, right? And we have an equation for the acceleration. Just divide the force by the mass. So that's going to be equal to 128 kqq, in this case x, right? All over d to the 6 times omega. Uh, Actually, that's it. So what happens? The x cancels out, right? So we just basically found our omega. Oops, sorry, I forgot a negative. They should have a negative here. Okay. All right. So with that, go ahead.
Is it because, sorry, for A, we use the F equation,
Yes.
the single of.
So let me just write that there. That's correct. F equals A equals F over M. Okay. We have an equation
Right.
for F, so we divide that by M. So there should be an M here, right? Okay.
Okay.
And then from here, the X cancels out. Then the negative sign also cancels out. We're left with omega squared is this thing, or omega equals square root of 128 kqq over md raised to 6. That's it. And again, put the value in the calculator. You are given your q's, your d's, and your m. And k is a constant. Okay.
Okay.
All right. Uh, you want to go to the final solution, or just you'll trust it's good enough?
I trust. I'll do it like after the class.
All right. So okay. All right. So we'll. The reason why I'm asking is I want to get through all the problems, as many of them today. Yeah. So all right.
Okay.
Okay. Let's do part C on the axis. Hold on. I'll copy the new. I'll copy this. Okay, but on the axis here, and we just ran out of space. Nope, a grid. All right.
Oh no.
Don't worry about it. We can still continue here. All right, but anyway, here, sketch the graph to show how kinetic energy varies with x. And then, D, the position is released. The object is released from position x0 equals 5.1 millimeters. Determine the maximum kinetic energy of the object. Okay, first of all, again, maximum kinetic energy is here. Minimum kinetic energy will be here. That should be easy for C. Yeah. And then, is it straight lines or curved? From what you recall,
Curved.
it should be curved. Okay. Okay. Something like that. That also means, even though it's not being asked, let's do this right away though. That also means that for the potential energy, you have maximum energy here, right? And then it's gonna go to 0 and it's gonna curve like that again. Okay. Uh, okay. So let's go to part 2 now. Okay, I'll just say red line is enough. This full answer. Okay. And let's note it here. Blue curve is the potential energy. Okay. All right. Let's go to part 2. You're given that you actually have an equation to do this, right? Okay. Which I cannot remember from the top of my head, so let me check the data booklet. Physics data booklet. Kinetic energy of harmonic oscillator. That's going to be okay. Where is it? Energy. Simple harmonic oscillator should be in HL. Here. Doppler effect. Here we go. Energy. The total energy. Here we go. I'll just copy the two equations. The two equations you will need are these. Okay, so these are the two equations. You already know what omega is, the angular frequency. You solved it from the previous parts, right? And then we're gonna use this, the maximum, what's the question here again? Maximum kinetic energy. We actually only need this because in this case, this should be equal to kinetic energy plus potential energy, right? Now, the thing though is when the kinetic energy is maximum, the potential energy is 0. So we're just gonna do EK, or kinetic energy, equals 1 half m omega squared x0 squared. Put our values in again for the mass, the angular speed, and this is gonna be the x0 you need. Okay. All right. Questions?
I understand.
Okay.
But
Go ahead.
regarding these formulas,
Right.
I never understand when to use which one, because if we have to find kinetic energy, for example,
Right.
we would do ET minus EP.
Yes, that's correct. It's always gonna be
But they're
like that.
basically the same. So it's just
No, no,
gonna be
no.
the change.
They're not exactly the same. They're similar, but not exactly the same. You see here in the total energy, it's x0. That's the amplitude.
Mm-hmm.
The EP would be wherever x is. Okay. Now,
Okay.
if the x here is the amplitude, then that means the kinetic energy is the total energy, and then the kinetic energy there is 0. Okay. However, I'm gonna give you an example here. All right. Let's do this in terms of a simple pendulum, but I'm gonna mark 3 positions on the path. Okay. So position 1, position A, B, and C here. B and C. Okay. So here at A, it's all EP, right? All potential
Yeah.
energy, right? Okay. So all we're gonna have to write here is that the potential energy here, this will be equal to 1 half m omega squared x 0 squared, right?
Yeah.
Okay. Here, it's also the same thing. The kinetic energy here is all that energy is kinetic energy. So that's also gonna be equal to 1 half m omega squared x 0 squared, because of conservation of energy, right? Now let's go now to this last part, position B. Here you have both, right? You have EK, you have both kinetic and potential energy present.
And is it half-half?
Okay, not necessarily. Not necessarily. I could put position B here, so to speak, or I could put position B right here. Anywhere in the
Right.
middle of the path, that's going to be the idea, right? But if we do
Mm.
that, even though it's not half-half, we can actually do it like this. This is going to be equal to the total energy is just going to be equal to potential plus kinetic. Again, just from conservation of energy. But now we substitute the values. Our total energy is 1 half m omega squared x0 squared, right? Our potential, oh, by the way, the x here will be this, okay? That's x, and our x0 will be there in this example. You see the difference
Okay.
between x and x0? X would be wherever the position is. X0 is definitely where
Oh,
is
it's
definitely the
understood.
amplitude. Okay?
Okay. Yeah.
Amplitude. Okay. Now in this case, we're just gonna write this thing again. That's gonna be 1 half m omega squared, but this time it's just x for the potential energy. And then if we can write the kinetic energy as 1 half mv squared if we wanted to, right? Okay,
Yeah.
so this is basically what it means. The total energy and the potential energy are only equal at the amplitude. Everywhere else, the potential energy is going to be less than that, less than total by this
Okay.
much, okay? And from there, we can use this to actually find out what the speed of that particle is.
Right.
All right, is that more clear now?
Yes.
All
Thank
right,
you.
great. Okay, let's move on. Next problem. We're done with that. This is done. Let's see. Okay, the next problem that we can do. Okay. All right, let's do some of the more simple problems for now, so we can maximize the time as well. Okay, so couple of long problems, then let's do the multiple choices. Okay. All right, let's start off with the ones we haven't done from last time. Okay. This, it's not okay. For this thing, it's actually quite easy to get. Okay. Okay. All right. So let's take a look here. One thing you will know is that we are looking at the force on Z, right? Okay. Now, which of those things is exerting a bigger force, X or Y?
We don't have the length, or
well, you can kind of see the distance.
It's the same.
No, X is close, and Y is closer to Z. Right? Imagine these are wires, because these are wires in the problem, right? So if you think about it from a different point of view, if you rotate your point of view, this is X, this is Y, and then this is Z. Okay? And again, from a different point of view, then X is carrying current this way, Y is carrying current that way, Z is carrying current this way.
So you're saying that X is not the same distance from Y that Z is?
It is. Not from Z. What happens here is this is a distance. Well, it doesn't really say what the distance is. Let's just say that's D, right? This is also D. That's what it's saying. But that means the distance between X and Z is 2D.
Right.
All right. So just look, not worrying about direction yet. Which wire is going to exert a bigger force? The closer wire or the farther wire?
On Y.
Okay, Y, right? Because it's closer. Okay. Now, this thing, I'm going to just tell you first, and then later, if you still don't know how I did it, I'll tell you. But for now, hold on. I'm just telling you what I'm doing right now. I'm doing a combination of the left hand rule and right hand grip rule. Okay.
Okay.
X is that way. Okay, I'm gonna show it on screen, but let me shift over the camera real quick. Okay. Let me just do it real quick first. So Z is causing a magnetic field to go like okay, current is going down, so magnetic field looks like this. So from Z's point of view, it's pointing away from the page. Then Z experiences that magnetic field pointing away from the page, and then the current is going down. So Z is gonna be repelled by X.
But
Follow?
is there like a theory that says if they go the same direction,
there's a shortcut, but that's the way I would do it if I forget the shortcut. But okay, I'm gonna tell you a shortcut, but this shortcut works if you think in terms of technology. Okay, the shortcut is think of a railgun. A railgun works. I'll just show you real quick how a railgun works. So basically, you have those two rails, and then you have a third piece of metal like that, and through that piece of metal, you have a current that's gonna flow that way. Okay, it doesn't matter which way the current flows, but it flows that way. It could go either clockwise or counterclockwise. But the important thing here is this is going opposite. Those two currents between the two rails are opposite each other, right? Now, in a railgun, these have to be supported because this kind of shoots out. This third piece of metal is going to shoot out like that. So this means this metal is going to shoot out like that, going to shoot out like that as well. In other words, if you focus on these two pieces of metal, the rails, they will repel each other.
Even though they have no current in them.
If there's no current, then they stop repelling, of course. But if there is current, because the current is gonna produce magnetic fields, those magnetic fields interact, they repel each other. Okay, so how is this useful for me? Because I'm gonna say that these two repel right away.
Oh, and they go opposite direction.
Yes, so that means X and Z should attract, right? Okay, now that's the shortcut, but in case the shortcut fails, do grip rule with left hand rule. Okay, grip rule for the source of the magnetic field, left hand rule for the one you're interested in seeing how it moves. So in this case, grip rule on X, left hand rule on Z. Then grip rule on Y, left hand rule on Z. Okay.
And with the grip rule, we only get which side it's coming out into the page or out of the page.
Yes. So it's gonna tell us which way it's gonna be like that. Okay. So anyway, so that's the shortcut. So we know which one's gonna be stronger. The repulsion's gonna be stronger. So the direction of the overall force will be left or right. So this is gonna be repelled by Y and attracted by X. But the repulsion is gonna be stronger, so
to the right.
To the right. So B and D are definitely out, right? Okay. Now you can also already say which one it is, because they have to subtract because of the directions of the forces, right? So if they're both F, which one can only be the result of a subtraction? If it's F plus F or F plus some fraction of F, it's gonna be C, right? But that means they're in the same direction. But in opposite directions, it's gonna be F plus some fraction of F.
Right.
So the only answer now is A.
A.
Alright. So that's the correct answer here. Without even solving for what F actually is. We just needed to know both the direction and the possible sum or possible resultant of the forces, which has to be less than F. Okay?
Okay.
Alright. Okay. Alright, so that one's done. Okay, moving on. Any questions there?
It's okay. I have to think about it.
The one you have to think about really is doing the left hand rule for force plus right hand rule for gripping. Okay, you need to practice that bit, but once you get used to it, we're okay. All right.
Yeah.
Rocket of proper length L moves with the speed v relative to the ground, and the photon is emitted from the back and is received at the front. The gamma factor of the speed is there, given. What's the time taken according to the observer on the ground? Okay, this should be easy because it's on the ground, right? In other words, we are gonna look for the length according to okay, so what's gonna be the length according to an observer on the ground? That should already tell us something, right? Remember, gamma as a factor is gonna be bigger than 1, right? Because we have gamma equals 1 over the root of 1 minus v squared over c squared. And the trick here to make it easier to remember is this is always gonna be larger than 1. Okay? With the exception of v equals c, right? Okay. Actually, even that. So if this is the case, and remember, we also know that the length will contract. So we want one with a factor 1 over gamma. Right? For L0. For L prime, right? So L prime will be equal to L over gamma. Right? Here's the thing though. If that's the time, how much and you know the speed of the photon is c. So how much time will the photon travel? The time will just the photon will travel a distance c over l, right? L prime. That's the first part. The photon will travel that much. If that is, if the rocket is stationary, right? But if the rocket is stationary, then L equals L prime anyway, right? So that means we're gonna have to add T prime here, okay? We're gonna have to add some factor here, okay? Because from the what's this? From the person on the land's point of view, that's what's happening. The photon's gonna travel, and then this is gonna travel. So later on, when the photon actually reaches the front of the, so I'm just gonna draw that this after some time t, right? So when the photon reaches the front here, like that, yeah, it takes a bit. Yeah, it's gonna be. We know that the time's gonna be dilated anyway, right? But in this case, okay, hold on. In this case, this is the time that the light will travel according to the observer on the ground. But this time is only for up to here, so to speak. If this is the L prime now, okay, we're gonna have to add this little bit here. So which one? What is this little bit here? This is just VT, right? So that the total length, the total travel distance of the light is equal to L plus VT. L prime plus VT, okay? So from there, we can already guess what our answer is. So that's a total travel distance. So the total travel time, according to us from the outside point of view, this is going to be equal to this total distance at c. Hold on. C equals L over T, and T equals L over C. Okay. Well, not L. This total distance traveled. Okay, and let's call this total travel x prime. So that's gonna be x prime over c. Okay, and then from there we can already see which one it should be. Because of the plus here, there's only one answer.
D.
D. Which again makes sense because okay, never mind that part. It will kind of make sense because of this extra time, extra distance that the light has to travel, the photon has to travel. Okay. All right.
Right.
Okay. Next question. Okay, hold on. How many more questions can we do? Probably two or three more. Okay. So, okay, this one's you're given this, the frequency, right? And then you're given the angular deceleration, f alpha, right? Here's the idea though. We need to convert this f frequency into an omega. And that's easy because that's just 2 pi. You just multiply that by 2 pi, right?
Mm-hmm.
Like that. 2 pi 2 pi f, right? And let's just put the actual frequency in here. That's gonna be 4 pi, right? And then we know the angular acceleration is equal to of course this will be in radians per second, right? So the angular acceleration is also given in 6 radian per second. So we have our angular speed, and to be specific, this is the initial angular speed. We have that. This is you're now looking for Well, we know it's gonna stop, so final angular speed is 0. Okay, and from here, we're looking for time. But what equation can relate all three of these things? What is alpha equal to? It's just a change in the omega divided by the time. Okay, now what's our change? It's just 4 pi. So now we're gonna put everything in here. This is gonna be 6 is equal to 4 pi over t. Okay, or from here, t is equal to 4 pi over 6, which is approximately 4 times 3 over 6. Let's just do the canceling out. We're left here with 2. We're left here with 2. T is approximately 2. What's our answer? That
A.
Okay. Sorry, that's the time it takes, right? Now, another thing we can do. Sorry, I misread that last part again. All right. So that's fine though. Okay. Another thing we can do is use kinematic equations here, because we wanna know what's this complete rotations. That's theta, right? Okay. So what's our theta here? Number of let's do theta. If we use our kinematic equations, that's S equals ut omega I t. Let's not use that. Let's use the other one. Okay, let's use the other one, that omega f squared is equal to omega I squared plus 2 alpha s theta. Okay. Now we know we also know that this is deceleration, so it's gonna be negative here, right? Okay. What's this? Also omega 0 0, so that means theta will be equal to omega I. Sorry, this is the one that's 0. Theta will be equal to omega I squared over 2 alpha. There's a negative sign. We put our values in. Yeah, that's it. We get our angles, right? Our angle of rotation. So this is gonna be omega is 2 pi at 4 pi. So that's going to be 16 pi squared. 16 pi squared all over 2. Alpha is 6. Okay. And what is this gonna be? We're left with that. It's gonna be 8. It's gonna be 3 and 4. 4 pi squared over 3. So 4/3 pi squared. Okay. So this is our angle. What's that in rotations? Remember, one rotation. Let's just convert that. One rotation equals 2 pi, right? So we're gonna divide this by 2 pi. So that's gonna become 2/3 pi, which is still approximately 2. So either way, we got 2, right?
Yeah.
Okay, so there we go. The answer here is gonna be A. It's just an estimate anyway, so that's okay. Yeah.
Okay.
All right. Can we do this last one? I think. Okay. Okay? Let me read this properly now. You have a tennis ball suspended above a pendulum like this. Oops. Tennis ball is held at rest above a bucket attached. Okay. The bucket and ball are released from rest with the string held taut from an elevated position. The ball subsequently lands in the bucket as the pendulum passes to its lowest point for the second time. Oh, okay. What's the approximate distance h between the initial positions? Okay. This is actually rather easy again, but what we need to go, this is gonna be the last one for today, I guess. We need to go to the data booklet again, because it's one of those formulas I haven't memorized. Okay, so let's just check it out. It's gonna be in where is it? It should be in D. Okay. Okay, let me see here. There, it's indeed the period. For this pendulum, this is a pendulum. The period is 2 pi square root of L over G. Okay, so it's given here that the pendulum, which is the bucket, swings twice, right? So we want a time equal to, so the time should be equal to twice the period. So that's gonna be equal to 4 pi square root of L over G, like so. That's the time this is the time for the pendulum to swing, right? And also, this time has to be equal to the time that the tennis ball will fall. So the tennis ball will fall in a certain amount of time. Which equation do we use? Which equation is best used here? It's going to be S equals ut plus 1 half at squared. This ut is 0 because it starts from rest. Okay, and then we change everything. So from here, h is equal to 1 half gt squared. G is the acceleration, right? And finally, t will be equal to the square root of 2h over g. Now, last thing is we're gonna put these together. So 4 pi square root of L over G is equal to square root of 2h over G. The G already cancels out because they're both in a square root, right? So what exactly are we looking for? We're looking for the height, right? What's the approximate distance height? So here we just work everything around. We just square everything first. We're gonna get 16 pi squared times L equals 2h. And therefore the height is equal to 8 pi squared L. Looking at our choices, what is the answer? What's the closest one? Is there anything I missed here? There's something I missed, haven't I? Oh. Two period, that's correct. This is correct. 4 pi 8. Okay. I may have missed something. Hold on. All right. With the string held taut. Okay, elevated position still correct. Oh, okay. Got it. There's something I missed. The period is, the time is not actually 2/3 of a period. So, not 2t. That's the mistake here. Hold on. Let's go back. Second time. Okay. So basically, this goes like that and like that. This is the second time it gets here to the bottom. This is just, the time is just 1, 2, 3/4 of a period. Okay. So yeah, that's the thing I missed. So we just change all this now. Period is there. 3/4 t, that's gonna be 3/4 pi. Okay, so let's just change all of that, 4 to 3/4. That should make it that should give us the final answer. Okay, all right, so while I'm just doing the math, any questions?
No, I understood it actually.
All right, great. So I think from here, just solve it and then done. Okay. Okay, so this is gonna be what's the change here? This is just gonna become 9/16. Okay, so from here, h is equal to 9 over 32 pi L. Yeah, which one's closest? Whatever it is. Okay.
Yeah.
Okay. All right. So okay. So any questions for today? I guess we can end it here for today for now.
Yeah.
Yeah. All right. We'll
Okay.
do the other two problems tomorrow and whatever else we haven't. Oh, actually, it's just the last two here. So we'll do these tomorrow before the next set. Yeah.
Okay.
All right. Oh, not tomorrow. Saturday.
Yeah,
All
I
right.
think so.
All right. So Saturday. So okay, I'll see you on Saturday. You have a good evening. Rest well. Okay. Oh,
Thank you.
quick
Okay.
question. Holiday
Yeah.
tomorrow?
I've had holidays since Friday
Oh,
last
since
week.
Friday last week. So yeah, I'm asking because you're in Italy from Catholic stuff.
Yeah.
Right. Okay. So
Oh, you
just
don't have the holidays, right?
in the Philippines we do.
Uh-huh.
Here in Indonesia we don't. We only have a holiday
Uh,
tomorrow.
oh,
All right.
okay.
Okay. So all right. You have a good rest. You take care now. Bye bye. I'll see you next
Okay.
Saturday. Oh, on Saturday. Okay.
Yeah. See you.
All right.
Bye
Bye bye
bye.
now. Okay. So that's the end of the stream. Hopefully that was useful again. Uh. Okay, those on the chat, if you're still there. Yep, again, we're doing review if you're still there. Yeah, sorry I wasn't able to check the chat. I was actually quite busy doing all the problems, showing how to do all the problems here. So anyway, either way, yeah. So again, it is exam season. That's why I think we're getting a lot of views, partially because of that. So yeah, I'll just end it here. So we will be doing this again on Saturday, same time. All right. So we'll see each other then. So, oops, I even forgot to actually go back to the board. Anyway, there are a few more problems here. So anyway, so before we go, don't forget to like, share, subscribe to the channel. We are on these social platforms. So we have uh, YouTube, Facebook, Instagram, TikTok, and Twitch when we go live. All right, so we'll end here. I keep saying that right now. I don't know why. I think I'm just tired. All right, so with that, okay, I bid you all now a good afternoon, good morning, good day, good afternoon, good evening, good night, wherever you are in the world. Stay freaky, everybody. See you on Saturday. Bye bye now.